Hey everyone, my name is Raphael and I am a senior at Northwestern and I'm studying computer science and computer engineering. For my 358 final project, I want to talk about Rust. Rust is a relatively new programming language which I think is super cool, especially in the parallel and high performance space. So, firstly, what is Rust? Rust is generally considered a systems programming language. It's strongly and statically typed, it offers memory safety without any sort of garbage collection, and it offers low to no cost abstractions for programmers. There are a variety of other safety and performance features as well. It started in 2006 as a personal project by Mozilla employee Graydon Hoare, who was frustrated with memory based software bugs in his building's elevator. It was officially sponsored by Mozilla in 2009, and version 1.0 was released in May 2015 and has since received many updates. So, what is Rust's value proposition? One of the main features of Rust is that it offers safety without any sort of garbage collection. Many modern languages like Go, Python, or Java all use garbage collectors to free up memory after it has been freed and is no longer held by any running process. This is both good and bad. It is good because it simplifies the programming model for programmers, but it's bad because it might introduce delays, especially in highly concurrent programs where one thread pausing might bottleneck the rest. Rust determines when a thread should be or when a piece of memory should be freed at compile time. You might be asking, what about the heap? Rust implements a system which is strict with pointers and ensures that a single piece of memory has a single pointer pointing to it. Once the pointer that is pointing to the memory leaves scope, it is freed using a special function called drop. There are also many wrappers that allow multiple pointers to look at a single piece of memory, and the compiler will know to only free that piece of memory once all of those pointers have been freed. So Rust does this safety using a variety of things listed below, like the compiler, what is called the borrow checker, lifetimes, and bounce checking. And I won't go too detailed into these, but generally speaking, the compiler was built around safety first. So it was built in mind considering all the features Rust wanted to support with regards to safety at compile time. The borrow checker is a system where, put short, there can be many readers or a single writer to a value. And this allows processes to sort of create these complex relationships without having too much complexity for the programmer. And I'll explain that more in the next slide as well. Lifetimes, I won't go too deep into this either, but it is generally a construct that allows us to track how long a value is alive and valid for. It helps us prevent use after free errors, double free errors, and things like that. And it ensures that if something exists in your program, it can be accessed and used. Lastly, bounce checking is kind of what it sounds like. We can statically analyze the boundary accesses of a array or anything to do with boundaries at compile time and make sure that we're not performing any out of bound accesses and causing any sort of memory faults. All in all, we produce performant code that rivals C and C++'s performance while ensuring safety. I won't go too deep into this, but this is generally a introduction to the borrowing of Rust. So we see the top left, we create a string and we move that string into B, where S is no longer the owner and we cannot use S any further. In the top right, we see the copy, which creates two values simultaneously. So we have I and we have J, and we can use both I and J later on. We have in the bottom left what is called a mutable borrow, where we can mutate the value of S with M using the and mut syntax, and we can perform different things with the string itself. And we have a non-mutable borrow, or just a borrow, in the bottom right, where we can perform some operations on the borrow, but not all, like the mutable borrow we see in the bottom left. So some general differences between the two, between some of the languages we've seen in C and C++. These languages are really fast, but we know they're prone to human error. We've all taken 211 in these classes that use C and C++, and we know that managing memory can be super tricky. Python, Java, Go, and other sort of higher level languages are relatively safer than C and C++, but they can be heavy with the garbage collector. Also, we might lose performance like we do when we use Python or Go because of essentially second-class abstractions that might make our lives more difficult in the performance space. With Rust, if it compiles, it will work. Basically, we want to get the best of both worlds within C and C++, where we have fast, performant code alongside the safety of other languages like Java, Python, and Go, with zero-cost abstractions that make programming easy for the programmer. So, basic parallelism in Rust is defined using two traits. So what is a trait? Basically, a trait is a set of methods that something can implement. So Basically, if something implements all methods in a trait, we say the thing itself implements the trait. So we have two main traits that we care about in Rust's parallel model. The first is send and the second is sync. For send, basically we can ask ourselves, can we transfer ownership to another thread? For sync, can we share this thing between threads? So you might recognize that this is pretty similar to the mutable borrow and immutable borrow we've seen in the previous slide. And on the right, we have a basic example where we use a thing called a RC, which stands for reference counter, which I mentioned before. We have these special pointers that allow us to have multiple pointers to a single piece of memory. And this is used by the compiler to determine when a piece of memory should be freed. The regular RC will not work in a thread case, as we see in the bottom, because it is not atomic safe, so it is not sendable. Whereas the ARC, which is the atomic reference counter, will work because it is thread safe and works across different threads. So this is a quick example of how to define a thread, spawn it, and do things with it. We have some other parallel primitives in the language that I won't get too deep into, but are worth mentioning. We have the multiple producer, single consumer. So this is sort of from Rust, where we are from Go's programming paradigm, where we want to communicate by share memory by communicating instead of communicating by sharing memory, which is sort of the traditional view that we take in C and C++. In the MPS CQ, we have a really strong use case for logging, for data pipelines, anything that has many consumer or many producers and a single consumer that we want to do work with. Other than that, we have a arc mutex t, which is a more traditional model where we might see what we might see in C and C++, where we have a mutex around some object t, and we have an arc around that mutex. So you can imagine that if many people are in a room, say your living room, and they want to change the channel, we might consider the remote to be the mutex, because the only person that holds the remote can change the TV channel. And the arc might be the living room itself, because once everyone leaves the room, we might no longer need the house itself, or we might no longer need the room itself. So we can then free the room. So quickly, I'm going to go into a small demo with parallel and sequential code. So firstly, I made some code here. It's pretty straightforward that calculates essentially an illustration of the Mandelbrot set. So I think we touched on this in class a little bit too. But basically, we're going to do some math that allows us to visualize different parts of the Mandelbrot set, which is essentially this complex equation that determines whether or not points blow up, reach infinity, when they reach a certain value, things like that. And I'll show a visual as well once this is completed. But generally speaking, the code creates some constants and creates a buffer, which for right now is going to be a buffer of size width times height. So in sort of the parallel way of doing things, we just want to create a single array, and then we put all our values in there. And then in the actual main for loop, we're going to do some math it's sequentially that basically allows us to compute the value in which the Mandelbrot set essentially approaches or balloons to, which can be visualized later. I then essentially create an image using this image crate, and this is defining the RGB colors themselves. And lastly, we have the file system here using a file create and a buff writer just to speed things up a little bit. And then basically we have also this function is inside Cardia, which is a small optimization that many Mandelbrot set calculators use to make sure that, or to check rather, if a value is inside of those two black dots, which I'll show you shortly. We don't have to compute it because we know it balloons. So the way you run things in Rust is we're going to go into the sequential directory and we're going to type cargo run. And what this will do is this will compile any of the packages that we use and also compile our main program. And we see here in about a second, we're going to see the time to compute. So this is the time it took to compute the actual image or the actual data in the image. And then lastly, we have the time to write the file, which takes about a second itself too. So here we see the image. It's pretty cool. We can zoom in on it a little bit and see different parts of it. We have a limited granularity just because of the scope of the programming itself, and I don't want this to run for 10 minutes to make a complex image, but this is pretty cool. And like I mentioned, we have these two dark cardioids in the middle where we can just skip computation entirely because we know it's going to be black. So if we now type cargo run dash dash release, what this does is this creates an optimized released version. So you can imagine this is essentially adding like the -03 flag like you wouldn't see. So if we compile it using the flag, we're going to see that the time to compute is likely around the same as it was before. So slightly less, but the time to write the file is significantly less. Like I said, this is essentially has to do with Rust's zero cost abstractions, where in the compiled optimized version, we are going to be leveraging a lot of these zero cost abstractions to do with the file system to make our file write time essentially 4 times faster than it was in the non-optimized version. Excuse me. So all looks good. Now we're going to introduce a crate. So a crate in Rust is essentially a library in C. So it is some amount of third-party code that somebody out there has written for the purpose of use in some sort of domain, right? So in this case, we're going to use a crate called Rayon. What Rayon is, it is essentially a single line of code for parallelism. So you can imagine we had OpenMP in C where we add a small sort of compiler indication of something we want to be parallel. In Rust, we have a very similar crate called Rayon, which allows us to do a very similar thing. The way it works here is we have a work stealing queue per thread. So each thread is going to be assigned some amount of work. And when they're done with their work, or if the queue is empty, they're going to look towards other threads to steal work that might be taking a long time. This is useful in the Mandelbrot case because we know the work is not distributed evenly, where some regions are going to be super easy and some regions are going to be pretty difficult. And it requires sendable and syncable objects to operate on, but generally these are taken care of by the compiler. We have the iter, which is essentially an iterator in Rust, which is a pretty common construct. It allows us to apply maps, filters, anything to do with collection, things like that. And in Rayon, we have what is called a par iter, which is the same exact thing, except it allows us to create a parallel iterator, which is able to operate in parallel. So we're going to have a quick demo here that introduces parallelism in our Rayon case in the same program and allows us to see how easy it is to add it. So if I put these two side by side, and I get rid of the side here, we're going to see the code itself looks very, very similar. We define the same constants, both on the sequential on the left and the parallel on the right. The only difference that you might see is that we have this for each loop here, which you can just think of as a for loop, where we have a buffer.parChunksMut. So this is our main driver of parallelism in this case. So we have a parallel iterator over chunks, which is mutable, of size width. So the mut here refers to mutability, which is important in terms of Rust's borrow checker. But for the case of the example, you don't have to really consider that. Generally speaking, we're just iterating in parallel over chunks that we specify with the width here. And you see inside the code is very, very similar with two main exceptions. The two exceptions being we write directly to pixel here and we write directly to pixel here instead of writing to the buffer like we did before. This helps avoid data races, which you might see in other languages. We'll see down here, any of the file operations remain exactly the same as before. But now if we were to access the parallel directory and we're to type cargo run, we're going to see it takes much, much less time, almost a 6-7x improvement. So this is all done just by adding these two flags seen here, or this one parallel iterator region seen here. So it is essentially a one-liner like you would see in OpenMP or any comparable crate or library, where we add a single line that allows us to then iterate in parallel without any other work on our end. There's no other difference in the code outside of introducing this one crate. So you'll see, again, if I add the release flag, we're going to see if our time changes, it slightly decreases for the computation, and again, it decreases significantly for the file time. And if we go in here and we look at the par round folder, you see the same Mandelbrot set computed. And for the sake of the demo, we can take the diff of the two images that were computed just to see if they're the same. And we see there's no diff, so they are the same, so they're computed correctly in both cases. Now we're going to quickly touch on SIMD. We talked about SIMD in class, and it stands for single instruction multiple data, and it is an optimization supported by many processors that allows us to compute many different operations in a single instruction instead of many. So in Rust, there are four main ways or strategies that we can use SIMD. The first is by using the release flag. So like I mentioned, the release flag applies a bunch of optimizations to the code, some of which generally and usually actually include SIMD. For example, it might unroll a sequential loop into fewer loops with more instructions per loop that allow us to use SIMD instructions. So if we have a loop that is 100 iterations, we might unroll it into 25 iterations, but we can perform one SIMD instruction with 4 pieces of data, effectively slicing the amount of loops by 1/4. This is generally done through LLVM, which I won't get too into, but it is a compiler strategy and a compiler backend that is a tried and tested technology that many, many compilers today use. The second option is by using vendor-specific intrinsics using std-arch architecture. So this is most similar to what you'd see in C or C++, where we have a set of x86, 64 SIMD instructions where we can specifically use those, but the program itself will only work on machines that have that specific architecture. So if we want to have a program run on ARM, RISC, and x86, we need to define essentially 3 if statements that determine which SIMD operation to use. Third, we have std-SIMD. So this is a work in progress extension to the standard library where we can, instead of writing, like I mentioned, 3 different SIMD instructions per architecture, std-SIMD allows us to write once a single SIMD instruction and have it work on any compilation target. So the idea is, instead of writing many different if statements on the architecture, writing code that might not work in some places, std-SIMD is an experimental crate by the Rust maintainers where we can write SIMD instructions once in a single architecture, regardless of what it is, and have it run on many different architectures. Lastly, we have a crate called wide, which I won't get into here, but it is essentially what std-SIMD is doing, but it is maintained by the community and is an additional dependency that people might want to avoid. So if we go into the example I have here, we'll see at the very top we have to introduce this feature because it is not quite finished and is not like officially released. And what we define here was we have 10 million elements and 16 lanes. So 16 lanes in this case, I used to define the width of our SIMD instruction. So for my Mac M1 Pro, it makes sense to use 16 given the size of the lanes and the SIMD registers that are available. So in A and B here, we create 2 different vectors of size, and we map their values as floats, basically just define the constants we're going to operate on. And we have a result in the scalar case and in the SIMD case. We time the time it takes in the sequential case, and then we use SIMD below. And I want to emphasize here how pretty simple this looks, right? We just have the SIMD here. From the namespace, we create this of float32 of 16 lanes, and then we just take from the slice. So this is just iterating essentially over 16 integers or floats each. And what we can just do here is quite literally just A plus B. So really simple. And again, this will work on any architecture. This will work on Mac. This will work on Windows. This will work on Linux. This will work on RISC, ARM, doesn't matter. The goal of the project itself is to have this code itself be compiled in such a way that allows it to run on any machine that supports SIMD to begin with. So if we go into this folder and we run the code using cargo run, we see that the SIMD case is over 4 times as fast as the regular scalar case. And what's interesting is if we use the release flag, as I mentioned, we see the times are almost the same because the compiler is probably optimizing SIMD into the instruction to begin with. And here are some sources, and that's the end of my presentation. Thanks for listening.